In this lesson, we are going to learn how to segment the blood vessels from retinal images. That means getting this from this image. If this is what you want to learn, please subscribe the channel and keep watching. In order to keep things organized, create a folder in the desktop or wherever you want. Name it Blood Vessel Segmentation in Retinal Images. Then create a folder named Test Images here. Open your web browser and search for Blood Vessel Segmentation in Retinal Images. Go to the image search result. Now collect 8 to 10 images like this. I have already downloaded the images which are copyright free and renamed them 1_left for left eyeball, 1_right for right eyeball, and so on. You should rename the images in this way so that you can follow the coding section properly. Now launch the MATLAB. Click on Browse for Folder icon and locate our working directory. Then click Select Folder. We are now in our working directory. Click on this New Script icon and save it as Main. Now we can start coding. First of all, we need to read the test images. We use imRead function to do it. We need to tell the function the location of the image. The images are in test images folder. Let's write the name of the folder. Then use a slash to get inside the folder. And we are going to experiment with 2_right.jpg. So write the name of the image. Now this function will load these images from test images folder. Let's store this image in a variable named test image. Now the test image is in this variable. However, it is a large image. To make the computation faster, we should resize it. In MATLAB, we use the Resize function to resize an image. Now we have to tell this function which image do we want to resize. We want to resize the image that is stored in test image variable. After that, we have to tell this function what should be the new size of this image. In a set of square bracket, we define the size. Let's resize it to 584 and 565 pixel. Now this function will return the resized image. Let's store the resized image in a variable named Resized Image. The pixel values of this resized image are integer. That means they cannot accept decimal points. However, as we are going to segment blood vessels which are very tiny, we need precision up to decimal points. That is why we need to convert this resized image into double data type. It can be done using im2double function. We need to tell this function that which image we want to convert. We want to convert this resized image. This function will return the converted image. Let's store it in a variable named converted image. This image is in RGB color space. We need to convert it to CIE lab color space. We can do it using RGB to lab function and providing the converted image as an argument of this function. This function will convert this RGB image into a CIE lab color space. Let's store it in a variable named lab image. The CIE lab color space was defined by International Commission of Illumination in 1976. According to this color space, the L represents the lightness of the color. The range of L is from 0 to 100. Here 0 means black and 100 means white. The A represents green to red starting from negative to positive. The negative value means green. The more the negative value, the greener it is. And the positive represents the red color. The more the positive value, the more intense the red color is. The B represents blue to yellow. The negative value of B represents blue, and the positive value of B represents yellow. Now take a variable named fill or anything else you prefer, then use cat function to concatenate 1, 0 and 0. Then add 3 here. This 3 represents the dimension of the concatenated arrays. Our image is in CIE lab color space, which have 3 channels. That is why we are setting the dimension 3 here. Now we are going to use the bsxfun function to perform element-wise binary operation between this fill and lab image. I think it makes sense why I created the concatenation of 3 arrays with 1, 0, 0. If we use add times operation here, which is actually element-wise multiplication, only the red channel will remain as prominent channel. Let's take a variable named field image and store the result of this function in this variable. Now we are going to reshape this field image. We do not want any particular dimension. That is why we are keeping this dimension argument empty and using 3 here because this is the existing dimension of the field image. Let's store the reshaped image in a variable named reshaped lab image. Now we are applying principal component analysis using PCA function where the argument is reshaped lab image. It will return the coefficient and score of principal component. We are storing this in C and S. Now we are reshaping the score based on the size of lab image. Store the new value of S in the S variable. Now we need all rows and all columns of the first channel. Here, the first column means all rows, the second column means all columns, and this 1 represents the first channel. Let's store this value in the S. It is time to convert the S into a grayscale image. First, we are subtracting the minimum value of S from S. Then, we are dividing it by the difference between maximum and minimum S. And the division is going to be an element-wise division. Here, this dot represents the element-wise division. Let's save the output in a variable named gray image. Now we need to perform contrast enhancement of this gray image. It is very easy to do it in MATLAB. Using adaptive histogram equalization function, we can do it. The first argument of this function is the gray image. We're going to apply the enhancement block by block. For that, we have to write num tiles, which stands for number of tiles, and the size of the block is going to be 8 by 8. Then we have to write n bins, which represents number of bins, and it is going to be 128. Now this function will return the enhanced image. Let's store it in a variable named enhanced image. The next task is to apply average filter on the image. To do it, we have to define the filter first. Using fSpecial function, we can define a filter. The first argument of this function is the name of the filter we want to use. It is average filter, and the size of the filter is going to be 9 by 9. Now this function will return the defined filter. Let's store it in a variable named avg filter, which stands for average filter. Now we have to apply this average filter to the image. We can do it using imFilter function. The first argument of this function is the enhanced image, and the second argument is this variable where the filter is stored. Now it will return the filtered image. Let's store the filtered image in a variable named filtered image. Then write figure, take the imShow function and put filtered image as the argument of this function and give it a title, filtered image. Now use imSubtract function to subtract enhanced image from the filtered image. Let's store the difference in a variable named subtracted image. Now we need to calculate the threshold level to segment the blood vessels. This program is becoming pretty lengthy. Let's create a function named threshold level. At the very beginning of the function, we use the keyword function, then a variable name which will be returned. Let's name it level. And then with an equal symbol, we have to write the name of the function, which is threshold level. And it will take image as an input. The function has been defined. First, the image is converted into unsigned integer using im2 unsigned integer 8 function. Then we use imHist function. The image is going to be the argument of this function. And this function returns the histogram count and the bin number. Now initialize a variable to 1. Then calculate the cumulative sum of histogram count using CumSum function. Let's save the result in a variable named cumulative sum. Now take a variable t indexed at I. Then take the sum of element-wise multiplication of bin number and histogram count. Then divide it with the cumulative sum indexed at the end. After that, round the t using round function. Now we have to find out the mean above t or MAT and mean below t or MBT. Find the cumulative sum for histogram count from 1 to ti and save the result in a variable named cumulative sum 2. Then find out the MBT by taking the sum of element-wise multiplication of bin number and histogram count indexed from 1 to ti, then divided by cumulative sum 2 indexed at end. To find the MAT, calculate the cumulative sum of histogram count from ti to end and then store the result in a variable named cumulative sum 3. Then find the MAT by taking the sum of element-wise multiplication of bin number and histogram count indexed from ti to end, then divide it by cumulative sum 3. After that, increase I by 1, round the average of MAT and MBT using round function and store the value in variable t indexed at I. Now create a while loop. It is true as long as it is more than or equal to 1. Now copy this entire block of code and paste it inside the while loop. This t indexed at I is the threshold. Store it in a variable named threshold. Finally, normalize the threshold and store the normalized threshold value in the level variable. Then end the function and save it. Go back to the main script. Now we can call the threshold level function. It requires the input image, which is the subtracted image, and it will return the threshold level. Now we can convert the subtracted image into a binary image using im2bw function. The first argument of this function is the subtracted image, and the second argument is the threshold level. Instead of using the threshold level directly, let's reduce the amount a little. For example, 0.008. This function will return the binary image. Store it in a variable named binary image. Then use the figure and imShow function to show this binary image as a figure and give it a title that says binary image. Let's run the code and see what happens. Alright, we've got something, but this is not an acceptable result. We need to remove these noises from here. Let's use the BWR open function to remove the noises from this binary image which are smaller than 100 pixels. Now this function will return an image without noise. Let's save it in a variable named clean image and use figure IMShow function to show this clean image as a figure and give it a title clean image. Save it and run the code. We got a much better image this time. Here are the segmented blood vessels. However, it is a binary image. Let's convert it back to color image. To do it, we have to take the complement of the binary image first, which can be done using IMComplement function. The input to this function is going to be this clean image, and it will return the complemented image. Let's use the figure and IMShow function to show this complemented image and give it a title that says complemented image. Let's run the code and see what happens. So this is our complemented image. Now we can colorize this image. In order to colorize the image, we are going to create a function named Colorize Image. The function will return color image, and the name of the function is Colorize Image. It will require 3 input. They are resized image, complemented image, and the color definition. In order to remain safe-sided, let's start by defining the default color. Here 111 means the default color is white. In case the users do not specify any color, white color will be used. Then if margin is less than 3, color definition will be set to default color. Here margin is a function that returns the number of input argument of a function, and this is the end of the if condition. Now force the complemented image to be a logical image. Then convert the resized image into unsigned integer using im2uint8 function and store it in a variable named resized uint8. Do the same thing for color space definition and store it in this variable. Now if the dimension of this image is 2, then this is a grayscale image. Here ndims is a function that returns the dimension of an input array. If it is a grayscale image, we have to initialize all 3 output channels with same values. The value of the red, green and blue channel will be this. However, in other case, that means when the image is not a grayscale image, we have to define the channels like this. And this is going to be the end of if condition. Now applying the color on complemented image, finally concatenate the red, green and blue channel into a 3-dimensional array. and this is the color image, and it will be returned by the function. This is the end of the function. Save it and go back to the main script. Now we can call this Colorize Function. The first argument of this function is the resized image. The second argument is going to be the complemented image. And the third argument is the color space definition. Simply putting 30 in a set of square brackets will be enough. It represents a color space with 3 channels. Now this function will return the colorized image. Let's store the result in a variable named final result. Then use figure and imShow function to show this final result as a figure and give it a title named final result. Let's run the code and see what happens. This is the image we got after filtering the original image. Then we converted it into a binary image. However, there were lots of noise here. After removing the noise, then we got a clean image. Then we converted it to complemented image so that we can apply color here. And this is our final result. You can see the blood vessels of retinal image has been colorized properly. That's all for this lesson. If you find this lesson helpful, please subscribe the channel, hit the like button and share it with your family and friends.